like maybe 5 people more, but maybe.
Hello, Gustavo. Or you not?
Hi, Marcelo. So.
That's hard. And I don't know if Israel has something to say or if his microphone is open just for me.
Yeah, well, yes. I don't know if Israel is saying something we're not hearing, right?
Oh, we have an answer.
He closed now. Yeah.
Just forgot the microphone open.
Okay, one more. I apologize. Let's wait maybe 2 or 3 more minutes to see if some people, maybe we get 15 people and then we start. Now.
This can be dangerous also.
Is anybody okay with that? I mean, can we wait? It's 14:06, so.
I just think someone else will appear, will show up. Just send some message or whatever. We can wait for sure, but do not fix a target that we don't know if we will be able to get it.
No, maybe we should just start, okay? I think, okay. So, I'm going to start with a short introduction. So, okay, let's start officially. So, welcome to the Matematica UFMG Live. I just make up that name. So, first of all, let me start with some announcements. Announcement 1. The organizer of the seminar, which is Eleno, let me be the host for today. So Eleno is right here, so I'm acting as a host, so I'm not the organizer. So thank you, Eleno, to let me do that. Remark 2 is that we have one person in the control room recording things, supporting the math. There's someone doing some screen casting, like recording our talk. Okay, let me pass now perhaps to the scientific program. Our speaker today is Niels Benedikter from Università degli Studi di Milano. Hello, Niels.
Hi.
Thank you for coming. Let me thank you again publicly for accepting the invitation. We are very happy you are here to contribute to our seminar, okay? Thanks again for accepting the invitation. I'm going to tell just 2 or 3, since you are new here, I think no one really knows you. I'm just going to say a few words about your work very briefly. So Niels started at the University of Stuttgart, right? Correct me if I say something wrong. Then he went to graduate school at the University of Bonn. Also spent some time at the University of Zurich during graduate school. After graduating, he moved to University of Copenhagen for a postdoc. Stayed there for a while, and then later he moved again to the IST, which is the Institute of Science and Technology in Austria, just near Vienna. Okay? Recently, he moved permanently, I believe, to the Università of Milano, where he's working right now. He has been working on mathematics of many-body quantum mechanics, and today he's going to tell us something about that. Okay, so I thank you again for coming. I'm going to pass the microphone to you. I'm speaking too much already here today. If someone, as I said, please feel free to interrupt. I mean, I think Niels will be happy to answer some simple questions during the talk. Otherwise, you ask something at the end. But please feel free to make your question. Okay, go ahead, Niels.
Okay, well, thank you very much for this nice invitation to Brazil, even if it's only virtual.
I forgot to ask, how was the flight?
Great, quick. Okay, so just a moment to let me figure out how I am presenting, right? So can you see my writing pad like this?
We are seeing your desktop, it's fine.
Okay, so if I write now, you can see.
Yes.
If I write the title, then you can maybe confirm to me that it works, because I'm using this program for the first time today. So my talk will be about effective theories in many-body quantum mechanics. Okay, so everyone should be able to see the title, I hope.
Yes, it's pretty good. Go ahead.
All right, perfect. Right, so Gustavo asked me to give a more introductory talk. So for the first, let's say, 2/3 of the talk, I will start with some very generic facts about about quantum mechanics. First, one particle quantum mechanics, then a very quick introduction to many-body quantum mechanics, some older results about effective theories, and if time permits, maybe the last 10 minutes, I will be able to speak about recent work from last year and this year. All right, so as I said, we start with one particle quantum mechanics. So I try to illustrate a little bit what the Schrödinger equation is. So we consider one free particle. And that means we consider an initial value problem, which is given by initial data, a so-called wave function, that is simply a function in the space L2 of R3. And we have an equation which is I time derivative of psi is equal to minus Laplacian of psi. That's the Schrödinger equation. And this is so far a very simple equation. You think of minus Laplace as being a self-adjoint operator in L2. So it's an operator valued linear first order ODE. It's easy to solve by using the Fourier transform. In Fourier space, the minus Laplacian becomes multiplication by k squared. So the solution of this equation is basically given by multiplying e to the minus ik squared t on the initial data psi naught in Fourier space. So the whole thing is solved by Fourier transform. The typical behavior you find is as follows. So I'll sketch to you the absolute value squared of psi naught. First of all, make a copy of this coordinate system for later use. Right? So psi naught squared, usually we would think of an initial data that looks like this. You have some position x naught on the x-axis. So let's see, I draw only one dimension out of 3. And you'll have some sort of bump around that. And you simply say physically the value here is understood as the probability to find a particle at this position x here. Similarly, for the Fourier transform of psi naught squared, an absolute value, so you call it the momentum representation. It's just the Fourier transform. You'll also find some sort of bump probably. Localized around some value p naught, say. And again, the value of this function here at the position p would be the probability to find a particle having momentum p. Now, what happens as we evolve in time, we go to t larger than 0, And the solution is going to look a bit like that. We still have the position x naught. Here I have psi t squared drawn. Now the bump will have moved, will be localized around a position that is roughly x of t being approximately x naught plus time t times p naught. But it also spreads out. So that's a very typical behavior of the Schrödinger equation. Sort of the bump moves essentially as if it was a particle of velocity, of momentum, p naught, but it also spreads out. So the probability to find a particle is going to spread out more and more as time evolves. Okay, so that's the one particle free Schrödinger equation. Now a little bit more interesting is the one particle in an external potential. In that case, the Schrödinger equation looks as follows. Again, you have an initial data psi naught in L2 of R3, but then the equation changes a little bit in that the self-adjoint operator, it's called the Hamiltonian H, is now given by minus Laplace plus a multiplication operator. So this part here is just multiplication with a function v external that goes from R3 to R. And like that, the equation is not explicitly solvable anymore, except for very special cases. Because the Laplacian is diagonal in Fourier space, the multiplication by Vx is diagonal in position space. So in general, you can't write an explicit solution for the equation. Still, it has a very typical behavior, and that behavior would be as follows. You draw a coordinate system here. And the third coordinate system. So what happens? I think of the example where my V external is basically a constant function on a stretch. I think of that as a sort of a wall. Let me copy this as well. So I have this wall modeled by the function V external. And now I make my initial data bump. And I let it fly against the wall. And what typically happens is at some point it's going to collide with this wall. Make some room here to draw. It's going to hit the wall, and inside the wall it's going to decay exponentially. So that here would be a time t0, time t1 later, and a time t2 even later. So what happens at even later time? Well, part of the wave function comes out again on the other side. Comes out here and continues to move, whereas the major part of the wave function is basically going to be reflected and move backwards. So this is this very typical behavior in quantum mechanics, this very typical behavior of the Schrödinger equation. If you let a particle fly against a wall, the major part of it is reflected, but some small tunnels through the wall and continues flying. This would be the very famous tunneling effect that probably everyone has heard at some point. I'll quickly check if there are any questions. No, I guess so far everyone's happy. All right. Now let's make things a bit more interesting and look at a system of n particles that interact with each other, not only with an external wall, but also among each other. So now the space in which things happen changes. Our initial data is going to live in an L2 of R3n now. Or maybe a bit more conceptual, you could think of this as being isomorphic to the L2R3 n copies in the tensor product. But you can simply think of it as a wave function psi naught of 3n variables. Or we group the variables together and we say it's a wave function of n particles, each of which has 3 coordinates. Now the Hamiltonian that we would typically look at for such a system is as follows. It's a sum of Laplacians acting on the coordinates of particle I plus potentially some external potential, also acting on particle xi, summed over all n particles. But then we add a real interaction now. And by real interaction, I mean something like this. So a double sum over all pairs of particles, and some function v that now depends on the difference of any 2 particles. So this is really an interaction between all pairs of particles. We say this is a pair interaction. It's still a multiplication operator, but it mixes different particles. Whereas this part in front here is basically the same thing we had as before. Up here, a minus Laplace plus v external acting in the same way of each of the n particles. Now, of course, if we put this v here, this function, equal to 0, this whole thing effectively reduces to a one-body problem because it's non-interacting. What does that mean? It reduces to a one-body problem. It means the following. Namely, you may start with a tensor product of wave functions in R3, right? So that just means psi naught of x1, xn is phi naught 1 of x1, phi naught 2 of x2, and so on, where each of the phi naught I live in L2 R3. But we can choose this initial data, and if we do so, it reduces to the one-body problem in the sense that also the solution is going to look like a tensor product. So each of these tensor factors is going to evolve in time, but you're not building up linear combinations of elementary tensors. And the way they evolve is simply by the non-interacting equation. So the ith wave function evolves by the non-interacting Schrödinger equation as before. By the one-body Schrödinger equation as before. So this would be the trivial case. Now, if the potential V is non-zero, then things get interesting. That's where our work starts. So for, excuse me, for V different than 0, well, then things get really complicated. In fact, in order to be able to say something, we have to be much more specific. In this generality with arbitrary psi naught and just saying V is different from 0, we may potentially describe almost the entire universe. We may describe semiconductors, neutron stars, whatever, human bodies, cars, CO2 molecules. To be able to say something mathematically, we have to be much more specific. And being specific means fixing a very particular physical situation, and the simplest physical situation we can fix is what we call a mean field situation. So the simplest case is a so-called mean field situation. What's typical for a mean field situation is all particles behave pretty much similarly. Meaning that we consider initial data that is a tensor product of n times the same wave function, what is called a Bose-Einstein condensate, BEC in physics. We look at high density, which means number of particles being very large, going to infinity. Let's say n tends to plus infinity. And the third ingredient, we look at weak interactions. And weak interaction means that we take this double sum that we have that defines the interaction term. And in front of it, we place a 1 over n. So this 1 over n here is maybe the most characteristic thing of this so-called mean field situation. You have this 1 over n in front of the interaction where n tends to infinity. You can think of that as balancing the kinetic energy given by the sum of Laplacians, because that's a single sum, that's sum over minus Laplace, so it has n terms in the sum, whereas the interaction is a sum over pairs, has n squared terms. By putting a 1 over n in front of the interaction term, we balance these things so that we can still expect to have a reasonable limit as n tends to infinity. Now, the advantage of this mean field situation is that since we have very many particles but very weak interaction, instead of many particles with individual collisions, we can think now about some averaging taking place, and simply one particle moving through an external potential generated by the cloud by the density of all other particles. So in this sense, you can still expect things to effectively reduce to a one-body problem, but with an effective potential in the equation. And that means the solution is still going to be approximately a tensor product, where the tensor factors, each by themselves, evolve in time, but you basically don't build up any linear combination of elementary tensors. And the equation for the individual factors is again a one-body equation. But you act additionally with an effective potential here in the equation. And this effective potential is, well, it's going to depend on how all the other particles are distributed. I'm looking at one particle moving through the cloud generated by all other particles. So I should see something like a convolution of the interaction potential with the density of all the other particles. Something of this kind here. Now you see, of course, this effective potential itself depends on phi t. So this one-body equation now is a nonlinear equation containing a term that's cubic in the wave function. And well, from a mathematical point of view, of course, that brings new difficulties, but it also has a great advantage, and that is we have broken down the problem to analyzing a nonlinear equation on R3 with 3 variables instead of a linear equation of 3n variables. And for example, if you want to do numerics, that of course simplifies life a lot. So we sort of overcame the curse of the tensor product dimension at the cost of having a nonlinearity in the equation. Oh, and I forgot to say this equation here is called the Hartree equation. So this has been rigorously established in the last 10 to 20 years by a lot of people like Spohn, Rodniansky, Schlein, Pickle, and many, many others. I can't name them all. So this is in all variations rigorously studied and a very well established topic. Let me take a quick look at the chat. No questions in the chat here. Okay, any questions here? If there are no questions here, I'll move on. Any questions? And then I'll move on to a somewhat more involved example and some more recent results. Not sure, did someone ask a question? No? Okay. So, more recent topics. That would be now dilute Bose-Einstein condensates. And what is known as the Gross-Pitaevskii equation. So, what does dilute mean here? Well, that means we look at a different physical situation now. And this physical situation is defined by looking at the following Hamiltonian operator H.
Niels,
Yes.
before you continue, we got a question. Gaston asked, does the effective potential on the Hartree equation depends on the initial data? No.
Exactly. On the solution. Yes, that's correct. It does depend. So I should maybe write V effective depending on phi t or something like that. Yes, it depends on the solution phi t. This is what makes it a cubic nonlinear Schrödinger equation.
Okay, thanks. So I think, yeah.
All right, so we're changing the Hamiltonian to describe a different physical situation in the following way. Namely, we write an interaction that has this maybe a little funny behavior on n. Well, what's the meaning of that? First of all, we've put an n squared in front of the interaction here, which means you have a very strong repulsion between particles. Or very strong attraction, but here we think always of V larger or equal than 0, so it's really a repulsion. And we have this n in here, which means that we look at a very dilute system. How can we understand that this is a dilute system? Well, think of all your particles being squeezed into a box. Say the side length of this box is fixed. We call it L, but it's fixed. Now we put a particle here and a particle here. Now, the support of the, let's say V is compactly supported, so the support of this function V here is going to be of inside a ball of effectively radius 1 over n. Same for the other particle. However, you have n particles in this ball, in this say box of side length 1. So the density is okay, so how to say it? So the volume that you have available per particle is 1 over n, but the typical distance between particles is going to be 1 over n to the 1/3. So the distance between these particles here is typically n to the minus 1/3. So as n is large, you see that the distance at which particles interact is much smaller than the distance at which they typically are. So they very rarely actually encounter each other. And in this sense, it's a dilute system. So you should also see that this is the opposite sort of the mean field situation. The mean field situation was high density, weak interaction. Here we have very low density, but very strong interaction. Still, we can try to make a guess for the effective equation that should be derivable here. So first guess. That would be, I simply write n squared v times nx as, well, 1 over n cubed v of nx. And then I notice that n cubed times v of nx converges as a distribution to a Dirac delta. You could say as n goes to infinity, this goes to 1 over n times the delta times the normalization constant, which is integral of v. You could conjecture that the solution is going to be again, the tensor product with equation I dt phi t being minus Laplace phi t plus, and now I simply put this Dirac delta into the convolution from before, and I would get a local nonlinearity like phi t cube multiplied by the constant integral v dx. Well, it turns out this reasoning is wrong. And, well, why is it wrong? The idea you need to have here is, roughly speaking, you have this function here that converges on a length scale 1 over n to a Dirac delta. And it turns out the solution, psi t, of the equation at the same time develops oscillations on whenever two particles, xi and xj, come close to a distance 1 over n. And somehow this ruins the convergence of towards the Dirac delta. So I will tell you the correct guess. The correct guess is as follows. The function psi t should really be approximated by a product over all pairs of some rescaled function g times the tensor product from before, which I will write now as this explicit product here. So the new thing is this factor here. The function g here is time independent, and in fact it was guessed quite early on by physicists this function should be solving the following equation, the time independent Schrödinger equation with boundary conditions fx tending to 1 as absolute value of x tends to plus infinity, and g being then f minus 1. Okay, so maybe that was a bit fast. I'll try to make a picture. Should think of x is along this axis, f is on this axis, and this is 1, this is the value 1. And the function f is roughly going to look like this sort of inverted bump. So this really takes care of the fact that when two particles come close together, they repel each other. So it's less probable to have them close together. And if you use this idea, this ansatz, then you can easily derive that the correct effective equation should be given by what I'm writing now. Again, a local nonlinearity, but with a funny constant now, 8 pi a, which turns out is smaller than the constant you would have guessed before. In fact, this a can be computed if you write the function f I drew up there as 1 minus a over x for at least asymptotically for large x. Now, of course, I didn't prove any of this, right? This is just a claim. If you would use this ansatz and look for solutions that follow this ansatz, then you would conclude this effective equation down here. In reality, that's also something you have to prove, that this ansatz here is correct, and that's of course that's the difficult work actually in deriving this effective equation here. The effective equation here is called the Gross-Pitaevskii equation. And rigorous work on that, well, has been done in recent years. So important, of course, the analogous time-independent setting has been studied by Lieb and Seiringer and Ingvarsson. I think these are some very well-known works. Then this time-dependent equation here has been derived for the first time by Erdős, Schlein, and Yao using the BBGKY hierarchy. Then later by Gustavo, myself, and Benjamin Schlein when we were all in Bonn. Using a second quantization method. And also by Peter Pickel with a counting excitations method, they call it. I would say these results are established, but not so long ago. And I mean, there are still many directions in the study of these dilute Bose-Einstein condensates that are a very active topic of research.
Niels?
Yes?
We have a question. I don't know, maybe you take a little break now, you made a pause. Carlos Humberto asked, if you look at the third, down to third question from below, maybe you want to leave that to the end. Is there a great interest in the trivial case without interaction with entangled initial states? I think he meant consider an equation with interaction points to 0 and initial data that is not of the product kind.
Right. That's a good question. Well, it can be studied due to the, yes, it can be studied due to the linearity of the problem. Right, so you would say if you have an entangled initial state, that's a superposition of elementary tensors. By linearity, you would say that's the Hamiltonian acting on each summand of the linear combination, and then you would be able to say each summand of the linear combination evolves as claimed. So, I mean, in practical terms, it might not be simple, but from a theoretical point, it would be clear what you have to do. You decompose into elementary tensors and you apply the procedure to each elementary tensor. Of course, the question how to decompose into elementary tensors effectively, those touch upon very other complicated questions also. I see that there's another question. I think I'll answer that right now too. In which sense exactly holds that the many-body wave function is approximately a tensor product in L2 norm? Right, that's another excellent question. In fact, not in L2 norm. That would tend to be a much too strong notion of convergence. So I was skipping these technicalities, but maybe I can sketch it quickly. But you would say in which sense psi P converges to, well, let's say either the tensor product or mean field, or this for Gross-Pitaevskii. This you have to use reduced density matrices to specify the sense of convergence. So the reduced density matrix would be basically you take the wave function psi t x1, x2, x3, and so on, times psi t x1 tilde, x2, x3, and so on, complex conjugation, and you integrate out all but the first variable. This would be an object that is called the reduced density matrix. And you can show that the reduced density matrices in this case converge. So the reduced density matrix defined by psi t, you would converge to the corresponding reduced density matrix defined by the n-fold tensor product. In pretty much all operator norms that you would naively imagine, like trace norm, Hilbert-Schmidt norm, and so on, Schatten norms. Right, but not in L2 norm. Okay, there's another question. What about two-body properties? Maybe you could specify a little more what you have in mind.
Yeah. I don't know, sorry, maybe he may, I don't know, Marcelo tell something else. Maybe he meant the second, or two-particle, maybe, I don't know if that's what he thought, two-particle reducible density, for example.
Well, you can also look at the two-body or k-body reduced density matrix. If you would integrate out n minus k particles, you have the k-body density matrix, and that for every fixed k, those converge as well, but for fixed k. That's the question.
Maybe we should, yeah, maybe we can get back to that later. Yes, I think he said yes. Okay.
Okay, so I mean, this would be the, let's say, rather general part of the talk. I thought I could still say about 5 minutes something about more recent work. I think, unfortunately, this is all based on second conversation, which I will not have time to introduce here. But I will try to sketch some ideas just for 5 minutes and then conclude. So I hope I'm not boring those too much. I don't know second conversation. Excuse me for that. So we have recently been studying another kind of effective theories, and I put this under the general concept of bosonization. And the idea here is that you take an interacting fermionic Hamiltonian let's call it HF, H fermionic, and you argue that for some limit n to infinity again, it would converge to a non-interacting but bosonic Hamiltonian. Which means you effectively solve the fermionic problem, since non-interacting problems are easy to solve, right? And okay, let me very roughly sketch the idea here. So we would look at something that is called the mean field Fermi gas, which in Fourier representation has the following Hamiltonian. right? So these A star operators here are so-called fermionic creation operators and fermionic annihilation operators. Those are operators acting on a Fock space, which is some particular Hilbert space, and satisfy canonical anti-commutator relations, meaning we satisfy this relation here, where P and Q are in Fourier space, so say corresponding to the torus, so Z3. Now what happens, what can you say about this system? So first thing you can say, if it's non-interacting, the minimizer is given by a so-called Slater determinant, the minimizer of the energy. So you would look at expectation of the Hamiltonian, which you call the energy. You minimize it with respect to psi, and you would find that the minimizer is a tensor product of plane waves and anti-symmetrized, because we're talking about fermions. And this index set BF here is simply a ball in K-space. So you would have K-space, Fourier space, which is Z3, or a lattice. You would take a ball around the origin that has radius picked in exactly such a way that you have n lattice points inside. So radius is roughly n to the 1/3. This is called the Fermi ball. Now, if you introduce the interaction V hat, then you cannot find explicitly the minimizer anymore. But you can make a nice observation, that is that the interaction can, up to some error terms, be represented by operators of the following form. Summing over modes that are in the complement of the ball, summing over modes H that are inside the ball, delta P minus H is, L. Like this. And these have a very nice property, namely, if you look at commutators of these operators, a BL with a B star K, you will find that it's given by delta KL plus an operator that is hopefully an error term. Why do I say hopefully an error term? Well, because if I just had delta KL, this commutator would exactly be a commutator as you expected for a system of bosons. So you would have a way of so I didn't write any of this, so interaction can be written using these operators. Okay, so you would have a way of basically rewriting a system of fermions in terms of new operators that are, up to this point, bosons. You would have found a solvable bosonic system, since of course something that is quartic in A star and A operators in terms of these pairs becomes quadratic, and quadratic Hamiltonians are non-interacting Hamiltonians and are explicitly solvable. In summary, it's a very rough sketched idea here. Now, of course, you have a lot of trouble with this epsilon KL operator, which is in fact an unbounded operator. So it's not even clear to say, what do you mean by this operator is small? But it turns out one can make sense of this notion of epsilon KL tending to 0 as n goes to infinity. And that way one can really prove that the minimum of the energy corresponding to this Hamiltonian can be obtained by solving a corresponding bosonic problem, a non-interacting one. So I will just try to sketch the theorem to conclude. We are able to say if the interaction in Fourier space is repulsive and compactly supported, the infimum of the spectrum of the fermionic Hamiltonian is bounded below by the infimum of a corresponding bosonic problem, expressed in terms of basically these B star operators I introduced above. And there's an error term here, so turns out n to the minus 1, n to the 1/3 doesn't matter. It's by an n to the minus 1/18 smaller than this inf sigma HB. And it's also bounded above by the same bosonic problem and another error term. Okay, so this was a little bit sketchy. This is very recent work together with Van der Naam, Marcello Porta, Benjamin Schlein, and Robert Seiringer in 2 papers, one from 2019 and one from May this year, where we proved the upper and then the lower bound more recently. Yeah, just to iterate, it's the idea of this story is a little bit different from the one I was introducing before. We're not looking at the time-dependent problem here. We're looking at instead at calculating the infimum of the spectrum. And we find that the infimum of an interacting fermionic problem can be computed by looking at a corresponding non-interacting bosonic problem. An explicitly solvable, almost explicitly solvable bosonic problem. And yeah, I think I'll stop at this point since explaining more about this problem would get far too technical. And well,
Okay.
Thanks.
Thank you, Niels. So if people want to, I don't know, if people want to open the microphone to get their hands up.
Thanks.
Can see it? Yeah. Thank you so much. Thank you for this nice lecture. Perhaps maybe people questions. We have a couple of questions. Maybe someone wants to say something else. Or let me see. Okay, thank you, Niels. Well, maybe I'll start with one. I have a quick question here. In the end, so go. Well, let's stop. Is there any? How this? So we have this infimum of the bosonic Hamiltonian, right, on the right-hand side. Right. How does that depend on the initial model of the fermion gas? I mean, is there a signature in the final result? Like, yeah, I'm not sure to say what I mean.
Well,
is there a signature of the original Fermi model in the bosonic Hamiltonian, or like?
Yes, absolutely. So there's an explicit formula for this infimum of the bosonic Hamiltonian that is, I mean, it's basically an integral. It's a complicated integral that involves essentially only depends on v hat of k, the Fourier transform of the potential that enters in the Fermi gas.
Okay.
Right.
We have other, there's one more question related to that. Maybe see the last question Gaston asked.
Right, is the infimum positive?
Which?
Okay, that
I don't know, does the infimum of the bosonic Hamiltonian, I mean, is the ground states positive? That's what he asked.
Yeah, so, okay, so in principle, yes, but what does that mean, right? Because well, I mean, what really matters is what's the sign of the difference of the two quantities? What is somehow the natural way of thinking about it would be to look at the non-interacting problem first, right? The one for v hat equal to 0, in which case you can do the minimization explicitly, and that one is positive. And then you can think of the infimum of the interacting problem is slightly lower than the infimum of the non-interacting problem. And how much it is lower is given by this infimum of the bosonic Hamiltonian.
Okay.
But in absolute numbers it would be positive. But right, the interesting question is, what is it respect to the non-interacting problem? And with respect to the non-interacting problem, you're lowering the energy by solving this bosonic problem. Because you could always take the state from the non-interacting problem as a trial state in the variational problem, in the interacting variational problem. And that would give you an upper bound, of course. So you're always interested in going further down with the energy by modifying the wave function. I hope that was comprehensive.
Okay. Any more questions, Umberto? Maybe, I don't know. Okay, maybe I have a quick question. Let's do maybe I'll make the last question, and then after you answer, we officially finish the talk, and then maybe if you want to stay 5 minutes more, we can chat a little bit more, okay?
Sure.
So my question is, you mentioned the mean field scenario, right? How did you call mean field situation?
Right.
Do you know the mean field situation is like, well, it appears 1 over n in front of the potential, right? Yes.
Right.
Do you know of any work that tries to obtain that 1 over n in front of the potential, like any kind of result that, well, you start with, anyway, do you know of any work that tries to justify in some setting the mean field situation? Like, I mean, I don't know if you understand my question. I think I suspect I make a very hard question. No, I suspect the answer is no, right? So, what I'm saying.
Yeah.
I was just asking if you saw something like that. I mean, is there any attempt of justifying, like, or if making it appear that 1 over n in front of the potential?
Yeah, it's a hard question, right? Of course, this mean field situation that we consider here is a mathematical idealization. In reality, in a physical system, you have a certain particle number, you have a certain interaction strength, and well, the interaction strength is usually not automatically 1 over n. So what one can ask is, can I make physical systems in which maybe I realize with 1 over n? It's an experimental question. And I'm not an expert, but I think that's sort of possible. Because physicists have this thing they call a Feshbach resonance, by which they can tune the strength of the interaction. But putting in some external magnetic fields, I think. I'm not sure about that. But you could, of course, use this Resumo resonance to exactly tune the coupling strength independence of the particle number. So
Okay, anyway, I think
good expression than a mathematics question.
I think my question was, thank you, it was more like a question, more like a comment too, because I think that I just made it was more like a very hard question. I'm not surprised that you don't have an answer. So, thank you.
I think there's another question.
There's one final question there for you. Maybe you can answer that. Someone, Gaston, is asking for a suggestion, I think.
Okay. Well, there's a small booklet with lecture notes actually. That is by myself, Marcello Porta, and Benjamin Schlein. I think it's Springer Lecture Notes in Mathematics, and it's called, I forgot what it's called. I could try to look up what it's called. It's something like many-body...
Effective theories on many-body... quantum mechanics,
I could quickly put a link in the chat. Let's see. Yes, here it's on the archive, so I will just put the archive link. Well, so there might be better reviews. I mean, this is the one I know best. So. I think maybe from your work there are some shorter review papers. Also from Benjamin Schlein, I guess.
Yeah, I think that there is one paper of fermionic and a review paper. Well, I can suggest to Gaston too about like near fields theory. It's a review paper publishing in a Colóquio.